Okay, good evening, everyone. Now we are recording. Um, so, are there any questions or concerns regarding anything we've discussed so far? Right. So, in the last and the very first lecture of this course, we talked about matchings and perfect matchings after a brief discussion about graph theory, right? And we ended with a particular question, which was a try it yourself problem, which is to define variables for the graph and write down some constraints. These will be linear constraints. We will talk more about them today, so that all the integer solutions correspond to matchings of the graph, and similarly for perfect matchings. So does anybody have a suggestion for this? Preferably someone who has not seen this in a previous course.
Sir,
Yeah,
I was
Harsha?
able, yeah, I was able to think something, but not completely.
Mhm.
Regarding the variables,
Yep.
maybe each edge is a variable, and we can
Right.
impose some constraints on it. Like if that edge is included in the matching, it will take the value one, and if it doesn't get
Great.
included, value
Okay.
zero.
Okay, so let me just do this. So this is a good start. Okay, so here is an idea: is introduce a variable, maybe we can call it xe, for each edge e of the graph G. Okay, and the intent is that we will have xe set to be 1 if and only if E belongs to the matching M. Here, M is a matching. Right? So our intent is to have this variable set to be 1 if the edge is in the matching. Okay? So how would we enforce this? So we have a variable for each edge, and we want to enforce, we want to somehow make sure that all the solutions to the system we write down, um, yeah. So we want to ensure that all the solutions to the system are going to be are going to correspond to matchings of the graph. Um,
So we
yeah,
could we
yeah. Go
need to
ahead.
have this constraint that for a particular vertex, when we add the xe for all the edges that are incident on it, it must be one.
Okay.
That vertex becomes
Okay?
only once.
Are you saying for matchings or perfect matchings?
Uh, okay. I think it should be for a perfect matching.
Okay. And what would it be for matchings? Because currently we are focusing on matchings.
It
Would it
can be
be?
zero or one.
It can be 0. Okay. So maybe I can write less than equal to 1.
Ah, yes.
Okay. So um, if I sum up all the edges incident at a vertex, if I sum up the variables correspond to this, right? So how do you visualize this? This is a vertex V, and we are taking the sum over all of these variables, xe1, xe2, and xe3. So we want this sum to be at most 1. Okay, all right. What else do we need? What other constraints do we need?
Like we need this for all vertices.
We need this for all vertices. Yes, you are right. So for every vertex, I meant, but I did not write that down. Thanks, Nitin. Okay. What else do we need? So can I take any solution to this system, and will that correspond to a matching, or do I need to specify more constraints? Can these x's be fractional? Can they be negative?
Like only zero and one.
Okay, so you're saying that all the x's should be 0 or 1. Okay, that's fine. So this is for all edges of the graph. Okay, so let's look at this system. We will talk more about, we will define things formally in a bit, but clearly these are linear constraints, right? On the left hand side, for each constraint, you see a summation of the variables. There is no product involved. So that is a linear function, right? For every vertex, you have one constraint. So if you have 6 vertices in your graph, like in this example, then you are going to have 6 less than equal to constraints. Okay. And each variable is required to be 0 or 1. Does everybody see why solutions to this system correspond exactly to matchings of the graph? Any solution. What do I mean by a solution? I mean an assignment of values to these variables. Any solution corresponds to matchings of G and vice versa. Let's take one quick example. So if this is my graph that we were looking at, and let's say we are looking at a particular matching E0, E4. Well, that just corresponds to setting these two variables to 1 and the remaining variables to 0. Right? So you've got 7 zeros and 2 ones. And this satisfies this constraint, all of these constraints. Does everybody agree with this? Are there any questions or concerns at this point? Okay. So if not, I'm going to rewrite this slightly, and I'll notice that this is going to not make any change. So I'm going to say that all of the x's are at least 0 and they are all integers. So all of the x's are at least 0, and I'm going to say that all of the x's are integers. Notice that this is the same as saying that they all belong to 0 and 1, because if any of them is greater than 1, then this constraint will be violated at some vertex, right? Because the sum has to be at most 1. So all of them have to be at most 1 because they are non-negative. Okay. All right. So I've just rewritten in this way. Okay. Good. So we are going to call this the feasibility integer linear program for matchings, and I will specify the reasons for each of those terms in some time. Okay, so ILP here stands for integer linear program. Okay, and we will expand on this in a few minutes. Okay, the point is every solution to this system is a matching, and every matching corresponds to a solution of this system. And this is a bijective correspondence, right? So for any two different matchings, you will get two different solutions and vice versa. Okay, so this is simply a different viewpoint for the matching problem. It is a more, let's say, algebraic viewpoint, if you like. Right? Rather than looking at from a very graph theoretical way, we are looking at it by introducing these variables and thinking about it in terms of these variables. Okay, good. Are there any questions or concerns regarding all the discussion so far? Okay. So What about perfect matchings?
Maybe we need to concentrate on summation.
So one.
Summation equal to 1, right? So we are only going to change this for the summation to be equal to 1, right? And if we make the summation at each vertex to be equal to 1, that just means that every vertex has been matched, and that would become the feasibility integer linear program for perfect matchings. Okay, so maybe I'll just make a note here. Feasibility ILP for perfect matchings, change the less than equal to 1 to equal to 1.
Sir, can
Yes,
we add one more constraint? Like, I mean, is it necessary something like adding all the edge variables to number of vertices by 2?
right. Okay. So is that so? That's a good point. So your question is that what if we add one more constraint? And what is the constraint again? You want to sum up all the variables, and that should be equal to.
Number of vertices, total number of vertices by 2.
Okay, great. So let us suppose we also include this, right? So we are going to change all of these inequalities to equal to. All of these will be equal to's, and we want the total sum of all the variables to be equal to n over 2. So should we include that or should we not include that? Why or why not?
Sir, this should be very trivial as it's the handshaking lemma.
Okay, okay, good point. So what do you mean by trivial again? Can you expand on
I
that?
mean, every graph follows this property of handshaking lemma. Okay,
Um,
I
that is
think,
if all the x's were equal to 1,
and okay, yeah,
maybe
true.
that's
Okay,
what you mean?
yeah, exactly.
Hmm. So it's not really the handshaking lemma, but maybe. So why should we add this? Like supposing you are saying that we should add this constraint. Why would you add this constraint? And if you say that you don't want to add this constraint, then why not? Anyone?
I
Uh,
mean, we have that constraint, right? Like for every vertex, summation x equal to 1.
Okay,
So
okay,
if
go ahead.
we add all those constraints, we get 2 times summation xt over all.
Right, right, exactly. So this constraint is actually implied by all of these constraints. If you add up all the equations, then you will get exactly that the summation of all the edges is going to be equal to n over 2. I'm going to give this as a do-it-yourself problem. So here is a do-it-yourself problem. Show that um, this constraint is implied by all of the other constraints. Okay, so this is a good exercise to try out. In case you're not convinced, please try this exercise. And if you're unable to do it, just discuss on Piazza. Okay, so because this constraint is implied by all of the other constraints, we are not going to add it because it's a redundant constraint. It doesn't change the set of solutions to the system that you have written down. Okay, so because of this, no need to add this. Okay, does that answer your question?
yes, sir. Yes.
Okay, so please give this a try, and it should be straightforward. Yeah. All right. So that's why we are not going to add it, because already by putting equations for every vertex instead of inequalities, we will get exactly the set of perfect matchings of the graph. So all solutions will correspond to perfect matchings and vice versa. Okay. So I'll just make that point here. All solutions correspond to perfect matchings. Okay, good. All right. So why do we care about all this stuff? Okay, so let's start with one example, a real world example where we actually need matchings. In fact, I'll give an example where we need perfect matchings. Okay. All right. So matchings and perfect matchings for that matter have actually been used in a lot of different areas, in optimization, operations research, in fact, in areas as theoretical physics. And I just want to give you one example. I think in the last 10 years or so, there was a Nobel Prize in economics related to applying matchings to the organ donation problem. Okay, so here is the organ donation problem, a simplified mathematical version of the problem. We are not going to get into biological and medical constraints and ethics, but just look at the very sort of core mathematical problem that is underlying this. Okay, so let's say you have a bunch of donors. I'm just going to give you a specific instance. So these are donors, and let's say you have some recipients. And let us simplify matters by having an equal number of donors and an equal number of recipients. Okay. And well, you see, not anyone can donate to an organ to anyone. You need various things such as blood group and all to match. And on top of that, depending on the specific medical conditions, two people may be highly compatible or they may not be as compatible, right? So we can think of that as some sort of a risk factor. Okay. So I'm going to put down some numbers here. So rho I, and maybe let me put rho di, and column rj, the entry in this place indicates the risk factor. Okay, so the lower the risk, the more compatible are those two people, the donor and the recipient. Okay, and in particular, if I put a hyphen, it means that the two are incompatible. You can think of this as being a risk factor of infinite. Okay. So for a particular donor to donate an organ to a particular recipient, they need to be compatible at least. Okay. And ideally, you would like to minimize the risk. Of course, you may not want to minimize the total risk in the actual real world setting, but here we are looking at a special case where we are just going to minimize the total risk, which is equal to the sum of all the risks that you choose. Okay. So the goal is to match all of the donors to, maybe I'll put it differently, to match each donor to some recipient so that the total risk is minimized. Okay, and I want to mention explicitly here that this may not be the best decision from a medical or a biological or a humane point of view, right? But that's an aside. Okay, so modulo that comment, let us focus on the problem we have here, right? So what does this correspond to? So first of all, notice that there is actually a way to choose donor and recipient pairs. So for example, if we choose donor number D3 to donate to recipient R0 and D1 for R1 and so on, the circles I've marked, then clearly you have actually matched all of them, right? Everybody, it just means that in all of the rows and in all of the columns, you have exactly one circled entry, right? So there is a way to do it, but can we think of this as a perfect matching problem? And I mean, it's a very straightforward formulation, right? Can anyone suggest what to do? Can we construct a graph from this?
I mean, it's a bipartite graph.
Okay, and what are your two parts going to be?
And one side is the donors and other recipients.
Okay, great.
And we have edges everywhere except for the dash.
Okay, great. So what we are going to do is we are going to construct a graph. We are going to put the donors on one side, D0, D1, D2, D3. And we are going to put the recipients on the other side. All right. And what are the edges going to be? Well, whenever a donor and a recipient are compatible, we are going to put an edge for that. Okay. So we are going to put all of the edges except D1 R0 and D3 R2. Okay. So this is with all of them. D1 goes to everyone except R0. And D3 goes to everyone except R2. Right? And observe that matching all of the donors and all of the recipients, it simply corresponds to a perfect matching in this graph. Okay? So our goal is to find a perfect matching in this graph and how do you make sure that the risk is minimized? So what is the risk corresponding to a particular perfect matching?
Summation of XC into the
Exactly. So for a particular perfect matching, the risk of that perfect matching is simply you take all the edges in that perfect matching and you add up the risk. Right? Perfect matching M such that the risk of the matching as defined here is minimized. Okay, good. So we not only have a problem where we want to find a perfect matching, now we have an additional thing going on here, which is the risk for that particular matching. So typically in the literature, it's called a minimum cost perfect matching, because in many applications, instead of a risk, you have a cost, because the applications come from, let's say, finance or economics or whatever. Okay, so that brings us to the minimum cost perfect matching problem. Okay, and how would we represent this? So I want to write down an integer linear program, which we are yet to define formally, for the minimum cost, min cost perfect matching problem. Okay, so we are going to write down the same constraints that we wrote down earlier. We are going to put an equation instead of the inequality, right? Because we are looking at perfect matchings. So we have variables for each edge as before, and for every vertex of the graph, we want the sum of the edges incident at that vertex to be equal to 1. We want the x's to be non-negative. We want the x's to be integers. For all edges of the graph. And we have one more thing, which is we want to minimize the total cost of all the edges that we have chosen. Oh, sorry, I think I forgot something. I forgot to multiply by the risk factor, right? We want the risk of the edge. So I'm going to put C of E multiplied by X of E, where C of E is the cost of edge E, right? And what is our input in this case? We have a graph and we have a cost for every edge. So G is our graph, and we have a function C that gives every edge of the graph a real number cost. Right? These are the edge costs. Yeah, go ahead.
Sir, should xe be less than or equal to 1 also?
Right. So why are we writing an equal to 1 here? That's because we know that our graph has a perfect matching, and we are trying to match every donor and every recipient. So yeah, if we were trying to find a maximum matching in case our graph did not have a perfect matching, then I would put down an equal, less than equal to 1 here. Right? But this is because we have, the graph has a perfect matching, and we are assuming that in our problem statement. Okay.
I mean, like, yeah, if we allow less than equal to 1, we always get zeros as the optimal answer.
That's a good point. Yes. So in fact, I made a mistake there. If you're trying to minimize the risk factor and you allow less than equal to 1 here, you will actually get the empty matching, assuming all your costs are non-negative, because then you will not match anyone, and that basically means that you're not taking any risks in life, quite literally, right? So actually, if you want to find a maximum matching with minimum cost, you have to do something more sophisticated. But let's not go into that right now. It might appear on one of your assignments. Okay, so right now we are just assuming that the graph has a perfect matching, and we want to find a perfect matching whose cost is minimum. Does that make sense?
Sir,
Yeah, go
can
ahead.
we tell that the graph has a perfect matching just by looking at the input which we have?
Good point. Right. So we will come to that very shortly.
Okay.
Okay. So I'll address that either today or in the next lecture.
Sure, sir. Okay.
Okay. So maybe I'll just make a note here. How do we decide whether a graph has a perfect matching? And I'll just make a note that we are coming to this later. Okay. All right. Good. Okay. So this is Notice that there is the key difference I want to point out. This ILP, integer linear program, that we have written down, it has an objective function that we are trying to minimize. So this here, what we are trying to minimize, is called the objective function. We want to find a perfect matching that minimizes this particular function. Okay, and this is different from our previous integer linear programs where we did not have any such constraint. That is why I call them feasibility ILPs, because we just care to find if there is a feasible solution or not. Okay, we are not trying to minimize or maximize anything. Okay, and that's why we are going to call this. So this would be typically called an optimization linear program, but we are not going to say that. We are just going to call it an integer linear program. Okay. So generally speaking, we are going to have an objective function, but it's also good to know that even after removing the objective function, there is a lot of interesting stuff going on. Right? Just solving the system is also an interesting thing to do. Okay. So are there any questions or concerns at this point? We have seen our first example of an integer linear program, uh, both the feasibility version and one with an objective function. And now I want to actually go into formally defining things now that we have seen one example. Okay. So before we go there, I want to make one more comment. So why do we care about all of this, right? Why are we taking a combinatorial optimization problem and then writing it down as an integer linear program? What's the motivation? So that's something I want to comment on. So what we will often do is we want to solve these combinatorial optimization problems, right? So we want to find an algorithm that, given an arbitrary graph with edge costs, will find a perfect matching of minimum cost, assuming that the graph has a perfect matching. Okay. So how do we solve this problem? So one way to do that, which we want to explore in this course, is to formulate the perfect matching problem, the minimum cost perfect matching problem, as an integer linear program. Okay. Then we are going to remove this integrality constraint and we are going to consider the linear program without the integrality constraint. So these constraints are called integrality constraints. Okay. So when we remove the integrality constraints, we are going to look at a problem that is more general because we are allowing fractional solutions. And that is going to be called the relaxation, also known as the LP relaxation of this problem. And then we are going to use linear programming theory that we are planning to explore in this course to solve this problem. Okay, so that brings me to LP relaxation, or just relaxation. In this course, we will only be looking at LP relaxations, so we don't need to say that. So take an ILP. For a given ILP, drop the integrality constraints. Okay, so in particular, for our problem, if we just remove these integrality constraints, we will get a linear program. Right? So this part here is our relaxation. Why do we call it a relaxation? Anyone? Any reason why we should call it a relaxation and not something else?
I mean, we
Yeah,
have
go ahead.
a large space to be able to.
Right. We get a larger solution space. So I want to point out at least one example. So let us consider, so let's, why? So let us consider the following graph. How many perfect matchings are there? Two. Only two perfect matchings, right? Which basically means two solutions for the perfect matching ILP, integer linear program that we wrote down earlier, right? Notice that here we don't care about the objective function. We are looking at the feasibility ILP, okay? There is no objective function. But how many, supposing I just look at the system, supposing I just consider for each edge, for each vertex, I want the sum to be equal to 1, and I want all x's to be non-negative, right? This is the relaxation of the feasibility IP. So how many solutions are there to this system? Can anyone give me a solution that is not a 0-1 solution?
Like 0.5.
0.5 for every edge? Is that what you are suggesting?
Yeah.
Exactly. Can you give me another solution?
I mean, we have infinite solution.
Infinite. Okay. So we can also put 3/4, 1/4, 3/4, 1/4. You agree? Good. The point is that you have way more solutions than if you were just looking at integer solutions, right? The integer solutions are simply the two perfect matchings. So you give 0 to the alternate edges and you give 1 to the other two edges, right? Whereas if you relax the problem, you remove the integrality constraint, your solution space grows in general, right? And that's the reason we are going to call this a relaxation, because we are relaxing the problem to allow fractional solutions. Why we are doing that, we will see that as we develop the theory of in this course. Okay. One final example. How about this graph? Maybe I'll give this to you as a do-it-yourself problem. So find all solutions for this graph for the corresponding, maybe I'll write it differently, for the perfect matching ILP for this graph. Okay, and prove it. Okay, it's an easy problem. So try to do this one.
So like one doubt. So do the values need to be rational or?
Sorry, I meant ILP relaxation. My bad. For the relaxation of this perfect matching ILP, which basically means what we have written down here. Okay, so for this graph, consider this system of equations and inequalities and find all the solutions. Is the question clear? So all the DIY and TIY problems will be posted on Piazza at the end of the lecture, either on the same day or the next day. So in case the question is a bit vague here, it will become completely precise in the Piazza post. Okay, but if there are any questions, please let me know right now.
No, sir. Like one small doubt. For this,
Yeah.
do we allow only rational numbers or any real?
Oh, I see. No, we are allowing all real numbers.
Okay.
Yeah, good point. So we are not restricted to rational numbers. We are allowing all the reals. When we develop some of the theory, we might stick to rational numbers. Otherwise, you just require more work, or sometimes the theory does not work out. But as far as this particular question is concerned, we are allowing all real numbers. Okay, good. Any other questions or concerns? All right. So We have been talking about LPs, ILPs, and all a bit just by this example. I want to make things precise, so let's do that. Okay. All right. Okay. So I'm going to define things for a fixed finite number of variables. So I'll set the number of variables to be 3, but whatever I'm writing applies to as many variables. Okay. For let's say you have variables x1, x2, x3 for the sake of example. So a linear function, as most of you would probably know, is any function. I'll generally abbreviate to this, of the form alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3, where the alphas are real numbers. Okay. Good. Notice that when we have a linear function like this, we can also write it in vector notation, which will be finding very useful. So we can write it as alpha 1, alpha 2, alpha 3 as a row vector multiplied by the column vector of variables. Okay. We'll be using vector notation quite a bit, so it's good to get used to it. Convention. So generally, if I say, I may write this down as alpha transpose x, because we are going to, generally our vectors are going to be column vectors, and when we want to indicate a row vector, we are going to take the transpose of it. Okay. So in general, the vectors are going to be column vectors, and we use transpose okay. Good. All right, and I would also like to define what is an affine function. An affine function is simply a linear function plus a constant. Okay. So, right, so it's basically a translation of a linear function by a certain constant. Okay. For example, it would be alpha 1 x1 plus alpha 2 x2 alpha 3 x3 plus some delta, where alpha i's and delta are all real numbers. Okay. And we can write this as alpha transpose x plus delta. Okay. Good. And what is a linear constraint? It's going to be any linear function less than equal to, greater than equal to, or equal to a constant. So it's going to be this way, or where f of x is a linear function for the vector x, right? We noted that here x is our vector x1, x2, x3. Right? So it's a linear function, and beta is any real number. Okay, so these are the three types of constraints we are going to allow. less than equal to, or greater than equal to. Okay. And finally, the most important thing, what is a linear program? It is an optimization problem of maximizing or minimizing an affine function. So we are going to allow the addition of a constant because clearly it doesn't matter, right? And sometimes when we are developing the theory, we might find constants useful. So that is the reason we are going to allow the objective function to be an affine function. Okay, so we are allowed to add a constant subject to a finite number. This is crucial. You can't have an infinite number of constraints. Finite number of linear constraints. Right? So this is what we refer to as a linear program, also abbreviated as LP. Okay. You might ask, why are we calling this a program? Is it something related to programming? Well, I'll tell you more about the history when we come to linear programs in the next module. But briefly, if I'm not mistaken, historically what happened is that if you use the term programming, you tended to get more money for your research. So rather than calling it linear optimization, people referred to it as linear programming because you just tended to get more money if you use that term. Right? This was back in the days of the World War II when programming was still a new thing. Right? So that's why they called it linear program, and we are stuck with that terminology. Right? But perhaps the more correct thing would be to just call it a linear optimization problem. Okay. Um, So the development of linear programming is very tightly tied with the World War II and post-World War II years. And we'll talk a little bit about the history, or I might give you some references in case you're interested. Okay, good. And what is an integer linear program? ILP. So it's simply a linear program where some non-empty subset of the variables are required to be integers. Okay, so an LP with the additional constraint that some non-empty subset are required to be integers, right? So this constraint will be called, these will be called integrality constraints. Okay. Good. All right. So that's all we have for now. I want to give you two examples. Maybe we'll discuss these tomorrow. So for now, just do it yourself. What about the following optimization problems? Are these linear or are they not linear? So instead of writing subject to every time, I might just write s dot t dot. And here are your constraints. So that's your first. And the second one is, okay, so are these LPs or not? Okay. So probably you already see the answer if you have followed the definitions, but just do it yourself and we can go over them quickly tomorrow. And after that, we will continue. We might go back to matchings and perfect matchings. Yeah, so that's all for today. If there are any questions or concerns, please ask.
Sir, I have a question.
Yeah,
Uh, so the problems we're trying to solve, the real world problems using these techniques, are there any other fields solving the same problems using different approach?
right. I see. So you mean, so these real world problems, many of them turn out to be combinatorial optimization problems, right?
Yes, yes.
So then I suppose that your question is, can these combinatorial optimization problems be solved using other techniques? Is that right?
Yes, yes, techniques other than this linear programming technique.
That's a good point. So for some of them, there are, so most of the combinatorial algorithms, so most of the algorithms that are there for, let's say, minimum cost perfect matching, or another problem we'll be seeing in this course is shortest path. Most of them are actually based on linear programming itself.
Okay.
In fact, there are many different ways of formulating their algorithms, but as far as I know, all of them are actually based on linear programming ideas. What happened in some cases is people actually found the algorithms, but the theory of linear programming was developed later. But the algorithms they found can be seen through the lens of linear programming.
Okay, okay. Got it.
So, in some sense, they are actually based on linear programming. Does that make sense?
Yes, sir. And why are we focused on these linear functions? Is it because the algorithms that were found, they are more suitable for these kind of linear functions, or if the function is not linear?
Right. Okay. So, well, okay. So, non-linear. So, in fact, it turns out that a lot of problems in the real world are actually not linear optimization problems. Right. I mean, that's bad news. So, you need actually theory to deal with non-linear optimization problems. Right. Um, However, the theory of linear programming is actually very useful in going beyond linear programming. Right? So once you have a grip on linear programming, you typically see why convex optimization. So for many problems, you have convex functions instead of linear functions, and linear functions are a special case of convex functions. Right? However, if you want to actually solve non-linear, arbitrary non-linear programs, that turns out to be incredibly difficult. Where you generally, if I'm not mistaken, you don't even have a lot of theory to solve these problems exactly. So the good thing about linear programs is you can actually solve them exactly, both efficiently in theory and also efficiently in practice. And sometimes these don't coincide. That's another thing we'll come to later.
Okay.
Right? But if you are actually interested in non-linear problems coming from the real world, then um, you sometimes need heuristic techniques, and you don't have exact techniques for them. To be honest, I'm not an expert on optimization, so beyond linear optimization is actually beyond my own scope. But my understanding is that you don't actually have exact techniques to solve non-linear optimization problems. However, the theory in linear programming is useful for understanding why nonlinear optimization problems are so much more difficult. And sometimes this theory can be useful to make some progress in nonlinear optimization. But yeah, I'm not actually an expert in nonlinear optimization. So one reason to study linear programming is because we can solve these problems. And it turns out that there are problems in the real world that do happen to be linear. And in that case, this theory is useful. But yeah, there is also a theoretical interest. So that would be the other way of looking at it.
Yes, I understood. Yeah, understood. Yeah.
Yeah. Okay. Thanks. Any other questions or concerns?
Sir, for a
Yeah.
linear constraint, does it have to be less than equal to, it will be only less than.
Right. So as per what we discussed, we are only going to allow less than equal to, and greater than equal
Oh,
to. Do you see why?
I mean, we want it to be a closed set. Right?
Exactly. Exactly. If you have strictly less than or strictly greater than constraints, then you may not even have an optimum, right? I mean, yeah. Yeah. So you don't want open sets. You want to get closed sets. That's the idea.
Sir, is it because at the edges we can still keep pushing the solutions if it is open set?
Sorry, can you repeat that point?
So the problem with the open sets is if it is open set, then we can keep pushing the solutions
Exactly.
at the edges.
Exactly. You can keep pushing it. You can keep getting better and better solutions. And so, in that sense, you don't really have a best solution. Exactly.
Sir, could you just explain what you just said? Like pushing the solution near the edges means?
Right. So, just consider the following example, right? Maximize x1, just x is one variable, subject to x less than 5. Right? What is the best solution?
Okay, it's like a limit. Okay, we can't get it.
Exactly. Exactly. So, that's the reason we are insisting on having less than equal to. We want closed sets.
So, but
That's the
if
idea.
we talk about, sorry, if we talk about we have an integer constraint, then a less than won't matter, I guess.
Right. That's true. So, yes, that's right. But because we want to actually go to linear programming and then use that theory, so if you have an integer constraint, right, then you might as well make it less than equal to by selecting the next integer, right?
Yeah, I get it.
Exactly. So in the case of linear programming, we are going to insist on closed sets.
Okay.
Yeah, exactly. In fact, all the linear programs that we are going to be particularly concerned with, they are going to come from integer linear programs by relaxing, right? Especially for the combinatorial optimization part of this course.
Sir, also, that word relaxing doesn't make sense. Doesn't it actually make the problem harder because we have a much broader set?
No, so the solution space increases. So in that sense, you are not making it tighter, but you're relaxing. But in fact, that's a good point. So it turns out that solving ILPs is much harder than solving LPs.
Okay, that was
So
not.
this might be counterintuitive if you are hearing it for the first time.
It is actually.
Solving LPs is easy, solving ILPs is much harder.
Okay.
Yeah.
Like, is it because we can use calculus in LPs, which you can't integer?
That is one way to look at it. On a more theoretical CS way of looking at it is that integer linear programming is actually NP hard, in case you are familiar with these concepts. But yeah, finding an integer solution is you can't actually use the techniques that you are able to use in linear programming. Yeah, but we will actually see proofs of things. So we might actually prove in the course that integer linear programming is an NP hard problem. For that, we might have to talk about NP hardness and NP completeness and stuff like that. Does that answer your question?
Yes, sir.
Okay. Any other questions or concerns? Okay, so feel free to leave the meeting. I'm here for another 5 minutes in case any other questions or concerns. So maybe I'll stop recording now.